All right, let's go ahead and get started. We are now looking at differentiability and continuity. Okay, so we've talked about these two topics last class, and we talked about continuity beforehand, right? We've already really dug deep into these two topics, but we're going to see how they correlate with each other, okay? So the following alternative limit form of the derivative is useful in investigating the relationship between continuity and differentiability. Okay. The derivative of f at c is as follows. It says f prime of c is equal to the limit as x approaches c of f of x minus f of c is equal to all over x minus c, right? It says note the existence of a limit in this alternative form requires that one-sided limits, in this case as x is approaching c from the left, is equal to the limit as it approaches c from the right, that they exist and they are equal. These one-sided limits are called the derivatives from the left and from the right, respectively. It follows that f is differentiable on the closed interval a to b if it is differentiable on a, b, and if the derivative from the right of a and the derivative from the left of b both exist. And then it says, if a function is not continuous at x is equal to c, it is not differentiable at x is equal to c. So we're going to go ahead and take a look at the first example. We're going to see that it is not continuous at x is equal to c, therefore it is not differentiable. Okay, so let's go and consider the function. It says f of x is equal to, and it has these double bracket x's, right? We've seen this one before. This is the greatest integer function, right? And so basically this one tells you that whatever number you are plugging in, you're going to round it down to the nearest whole integer, right? So I think on your limit maze, I gave you the example. If I plugged in 3.2 into this function, it's going to round it down to the nearest integer, which is just 3, right? So we're going to see as we're building up this graph, we're going to see that there's jumps and that it kind of looks like horizontal steps. Okay, so from the left side, there's a closed circle and then an open circle on the right. Okay, so here we go. If I'm starting at the origin, I'm going to have a closed circle at 0, 0, build up my function, and there's an open circle at 1, 0. And then it's going to go up to 1, 1, closed circle, to the right, open circle. And then I could keep on building this graph. And it looks something like this. Okay. So we are trying to find the derivative from the left and the derivative from the right. Now we found out that the derivative just really means the slope, right? This one's a little bit different though. I am going to look at it graphically, right? If I'm approaching x from the left, right, as x is approaching 0 from the left, it looks like we jump down to the constant of -1. So therefore, my limit is going to be -1, right? From the derivative from the right, I'm going to go ahead and see as with x is approaching 0. From the right, it looks like my derivative is my constant at 0, okay? So therefore, right, we see that the overall derivative or the overall limit does not exist because these two are clearly not equal to each other, right? And then we see that it's also not continuous, right? Because we see these gaps, right? Because of these horizontal steps, right? We see these little gaps. So therefore it's not continuous. If it's not continuous at x is equal to c, then it's not differentiable. And we see that it's not differentiable because obviously -1 and 0 are not the same value. So therefore, the derivative does not exist at x is equal to 0. Okay, but let's go ahead and look at example 6. So although it is true that differentiability implies continuity, the converse is not true. So that is, it is possible for a function to be continuous at x is equal to c and not differentiable at x is equal to c. So this is going to be an example where that takes place. And we're going to see this sharp turn, okay? So it says the function f of x is equal to the absolute value of x minus 2 is continuous at x is equal to 2. So the absolute value, we know the parent function. It looks like we're going to go right to. So I'm going to go and start building up my graph. And the absolute value function is, we're just stepping up 1 on the right, and then same thing on the left. So it looks something like that, right? And so we're trying to see if it is continuous at 2. Right off the bat, I can say yes, right? My graph is continuous because there are no gaps. There are no jumps from each increment, right? So it is continuous, but we're going to see if it is differentiable. So to find the derivative from the left, I'm going to go ahead and look at my graph. Now this one I can go ahead and actually look at the slope. From the left, it looks like as we're approaching 2, right, we're going down. We're going into the negatives. So my slope from the left is -1, right? Because we're going to go ahead and start here. We're going to go down 1, down 1, down 1, right? That makes sense. My slope from 2 to the left is -1. If I'm looking at my slope as x is approaching 2 to the right, right, we see that my graph increases. So this one I'm going to go ahead and go up by 1. So therefore, from the right, my limit is 1. Although it is continuous, it is not differentiable at x is equal to 2, right? Because we have different values. So therefore, f is not differentiable at x is equal to 2. And the graph of x does not have a tangent line at the point 2, 0. Okay. All right, so let's go ahead and look at example 7. So it says a graph with a vertical tangent line. So this is what I'm actually going to go ahead and apply the limit statement. So it says the function f of x is equal to x to the cubed root. So I can go and rewrite this like that. Is continuous at x is equal to 0. So I'm just going to go ahead and start. So there's the limit as x is approaching 0, right? I have f of x, which I know is x to the 1/3, minus f of 0. So I'm going to go and plug in 0 for x all over x minus 0. If I keep going at the limit as x is approaching 0, I'm going to keep the x to the 1/3, the minus 0, x minus 0, right? Limit as x is approaching 0, this becomes 1 over x to the 1/3 over x. Looks like I am dividing, so I subtract my exponent. So this becomes x to the -2/3. I can keep going the limit as x is approaching 0. This becomes, 1 over the cubed root of x squared. And then here's when I can go ahead and plug in 0, so use my direct substitution. This becomes the cubed root of 0 squared, or in other words, 1 over 0. Therefore, it is undefined. Right? So as x is approaching 0 in this case, it has an undefined value. So therefore, at x is equal to 0, there's a vertical tangent line. Vertical tangent line. Now, if we were to go ahead and graph this function, I just went ahead and graphed it on Desmos. There's my graph. It looks like an S. It looks like an S. So here's my graph for that guy. And let me go and move this down a little bit because it should be more towards the origin. Cool. So there's that graph, and we see that yes, as x is approaching 0, there's this vertical tangent line. There is this no solution, undefined value at x is equal to 0. Okay, so here is this little sharp turn, and therefore you can conclude that the tangent line is vertical at x is equal to 0. So therefore, f is not continuous, or not differentiable at x is equal to 0. Okay. It says a function is not differentiable at a point at which its graph has a sharp turn or vertical tangent. So this one became a vertical tangent line. In example 6, we saw that this has a sharp turn. Sharp turn going from the -1 value to the +1 value. Okay. Now there is a theorem, so it says if f is differentiable at x is equal to c, then f is continuous at x is equal to c. So in other words, if differentiable, then I could say yes, continuous, right? Then we have if continuous. This does not mean, so not necessarily differentiable. And I did not say differentiable. Okay. These are completely different things. So if differentiable, then yes, continuous. If continuous, this does not mean that it is differentiable, right? And that basically sums it up. If a function at f x is equal to c, then it's continuous at x is equal to c. So differentiability implies continuity, right? Those are the key words. Differentiability implies continuity. Continuity does not imply differentiability. And that's it for today's notes.